In this example, we're going to look at a related rate problem that involves an angle. Now just remember, if we're involving angles and taking derivatives, it needs to be done in radians. So that's why this problem is actually set up by giving us this in radians rather than in degrees. So what we're looking at in this problem is a balloon raising off the ground. It's staying above, so we're assuming that this is raising vertically. It's going straight up. So the person standing over here with a rangefinder finding the angle for this is standing at a constant 500 feet away from that. Now that's important to remember that this 500 feet is a constant. We'll get back to that in a little bit. The height is changing as this increases. Now we want to know about this when the height Now notice we don't know what the height is, so we'll put a question mark on that. Maybe we'll come back to that. What we do know is the rangefinder's elevation. So we've got an angle here for theta. This is not a constant. As the balloon rises, this angle is going to be increasing. What we're doing with this pi over 4 here is we're freezing this picture in time, but we can't really do that with our formula. Again, we'll come back to that. We also know that the rate of change here is 0.14 radians per minute. Since that's the rate of change of our angle, we'll write this as d theta dt 0.14. This is increasing, so we'll write that as a positive value. So the next thing we need to do is create a formula that connects this. Now notice the rates will not be a part of that formula, but we can connect theta to h. Since we have 500 here, we can write this as the tangent of theta is equal to h over. Now notice this is where it's important that this is a constant. If this was a changing value, I would need to use a variable here, but since it's a constant, I will plug it in now. At this point, we can go ahead and take a derivative. So the derivative of tangent would be secant squared theta, but we have to use the chain rule here, so times the derivative of the inside. Remember that this is implicit differentiation, so d theta dt. The derivative of h would be 1, but don't forget again, dh dt. Now we need to think about what we're actually asked to find, and we're asked how fast is the balloon rising. So what we're looking for here is dh dt, rate of change in the height of the balloon. Now let's look back at a couple other things. For one thing, I mentioned before, we do not know our height. It doesn't actually matter because we don't have it here. Kind of the idea of this, of using rangefinders, we don't actually need to know the height. So but what we do know, we know theta at this moment. Before we couldn't plug it in as a constant like this. We had a constant, we could put it in the original formula, but this theta is changing in this problem, but now that we're finding a specific moment, now is when we can plug it in. Part of the reason for that is that it's connected to d theta dt at this time. We needed to differentiate before this so that we could get a rate of change here, and so now we can plug that in. I could go ahead and move my 500 over to this side. And if we plug that into our calculator, we'll find dh dt to be 140. At this point, we need to put units with that. We do not have a correct answer until we've interpreted everything and with the correct unit. So we come back, we're changing, everything is measured in feet and in minutes. Okay, so our height is feet, which we see here with a 500 per minute. That's our rate of change in height. That's how fast the balloon is rising.